It is working, so if in case there is something not working from home, please get in touch. All right, so we go to the practical things related to the application of damping. We were speaking about the application of a concentrated damper, and we worked some ideas about the possibility that the concentrated damper is coupling the modes, and we explained all of that. And now what we want to do is to make clear that in case the coupling of the modes is not very relevant, then it works, the damper, it works adding non-dimensional damping, increasing the intrinsic non-dimensional damping of the system in the specific mode that we are looking at. So now I want to figure out, to focus that I am using this damper. I am looking, for example, to the second mode of a beam, all right? And concerning this beam, I already made the study of the free motion, understanding which are the natural frequencies, which are the modal shapes, and which are modal mass and modal stiffness, all right? So we know the quantities modal mass associated with mode 2. We know the quantity modal stiffness associated to the mode 2, all right? Now we know that adding this damper, we are building here a set of quantities that are associated to, for sure, the mode 2 with a specific damping for the mode 2 that is increasing the intrinsic non-dimensional damping of the mode 2, and so that we will look at, for the mode 2, a damped behavior like that, all right? So for sure we are expecting that because of the addition of this damper, the mode 2 on which we are looking at, so we are focusing on that, and we are expecting that the mode 2 is going to be dampened, all right? But we also know that because of the fact that there is a work, a virtual work of this damper also on the displacement of the other modes. And so this virtual work is not null, so that when the other modes are moving, so when the principal coordinates of other modes, for example, the principal coordinate qi is moving, for example, because the mode I is moving, I have an input of work into the equation of the second mode, all right? And so we know that it is, so there is some noise getting into. So it is not totally clean, the behavior of the mode 2. It's not just purely the mode 2 that will survive. So what will happen is that together with the mode 2, we will look at the increase of some, let's say, some noise coming from the other modes, all right? And so it will be difficult to excite just the mode 2 into a free motion. So it will, so this behavior like that will be somehow less clean because of other additional frequencies that are building up. But let's a little bit forget all of that. So we know that the equation will look at other components here that are associated to the other modes. But as a first hypothesis of analysis, let's not consider all of that, and just let's consider in which way we are measuring the effect of damping of this concentrated damper. So I want to give an answer to the question, which is the non-dimensional damping that is expected on this mode because of the addition of that damper in this location. So I would like to have an answer to this question. So in case it was possible to consider a simplified representation of the modal behavior of the mode 2, just forgetting the inclusion of the other dirty terms, let's say, you know, when I'm writing an equation like that for mode 2, which are the numbers and which is the effect in terms of non-dimensional damping of the mode 2, all right? So it is necessary that we are familiar with the possibility to understand the representation in terms of the non-dimensional damping. And so in my opinion, this is an interesting small exercise in which we clarify things that should be very clear, but let's say that we are repeating. So that the equation is written in this way. So the number R star 2 that was calculated here is written in this way. So it is the damping characteristic of the damper multiplied by the modal amplitude of mod 2 at the location xj twice. If we are working out the equation using the dissipative function, we are right in this quantity, all right? And so this is a known quantity, but which is the non-dimensional damping? So we must be aware that we have, I prefer to write the equation in the following way. So writing the equation dividing everything by m star 2, so that here it appears the natural frequency. So here I will have in the position, in the term depending on the displacement, I will have omega 0 star 2, all right? The natural frequency of mod 2, so I will have omega 0 2, omega 0 square 2 in this position, all right? Dividing, here I have nothing, I have 1, all right? And in the other side of the equation, I will have 1 divided m star 2, multiplying the Lagrangian component of the external forces. If I am working with free motion, this is cancelled, but let's remember that if I want to write the equation in this way, in the other side, I have 1 divided mass. And then here I write R, the dimensional damping, R star 2, then 2. If the problem is diagonal, we forget to put the double line index. See, this is the index 2, 2 on the principal diagonal. And so usually we write R star 2, that's it, because it is on the diagonal, right? If we are not looking at the extra diagonal terms, we have the modal mass for the mod 2, the modal damping for the mod 2, the modal stiffness for the mod 2, but for sure it is a double index here. It is in the n degree of freedom problem, it is the index 2, 2, all right? All right, so I have to divide the dimensional damping by the critical damping, then multiply by the critical damping, and we must know that the critical damping is 2 times the mass multiplied by the natural frequency. Why? Because we know it. So it is not necessary that now I go into the details for which reason the critical damping has this value. We cannot, we must know it, all right? I don't go more in details about that. So I am dividing by the critical damping, indicated like that, to the quantity, the dimensional damping divided by critical damping, I give another name that is non-dimensional damping, all right? I write that all of that is multiplied by the critical damping over here, because I have to multiply and divide by the critical damping. Then I divide by the mass, because I did it. And so this is canceling that. And so finally the equation, of course, I think that most of you know perfectly, it is written in this way, Q dot 2 plus 2 times the non-dimensional damping associated to mod 2, multiplying omega 0 of natural frequency of the mod 2 undamped natural frequency of mod 2, Q dot 2 omega 0 squared. And that's it, it's finished. All right. So this is the equation. Of course, the equation is written always in the same way. So we could have written this equation from the very beginning, because we know that the equation of the 1 degree of freedom system is written in this way. The only point is we have to give a number to this quantity and a number to this quantity. So we are working with the 1 degree of freedom system. The equations are always exactly the same equations. The only point is to put the right numbers into the equations, all right? And so this one is the natural frequency that is coming from the solution of the free motion of the problem. So from the free motion of the problem, the second mode is giving this quantity here. But then the point is which is the non-dimensional damping associated to mode 2. And so it is interesting, in my opinion, to write the quantity, and so to be aware that doing this calculation, we calculated what we did in the last lessons. We made the dimensional damping associated to mode 2 positioning of the damper at a certain location where the mode has an amplitude that is phi 2 function of the location where it's applied twice, multiplied square. But then below the fraction line, we have the critical damping. And the critical damping is 2 times the natural frequency of mode 2 and the mass of the equation 2. The mass of the equation 2 is the modal mass of the mode. All right? So this quantity here goes behind here. All right? Is divided, and it is, and so this is the modal mass. And the modal mass of mode 2 is written in the way that we learned, that is must be written. It is the distribution of mass scaled by the square of the modal shape associated with mode 2. All right. So we must. So there is nothing very very difficult. All of those are things that we know. We know those things, but we must be aware. So be prepared to answer to the question, all right, in which way I can write the non-dimensional damping that is expected to work in the general mode of this structure where I am positioning a damper in a certain position with a certain inclination or whatever, all right? We are applying concepts that are simple concepts that are coming from the previous lessons. All right, then we must be aware that the way in which is decaying the system in case we do not have an extra contribution of the other modes, and then we will discuss a little bit what we are speaking about of the noise coming from the possible other modes. And so this is the behavior. So there is a modulating damping function that is written in this way. This is we must know that the amount of damping is given by the expression E exponent minus non-dimensional damping. It is very important to know this number. So from the quantitative point of view, we must write a number here. We must be able to write the numbers. It is necessary. But in the analytical expression, it is multiplied by the natural frequency omega 0,2. In case we do not remember those expressions, there is only one thing to do. Go back, theory of the 1 degree of freedom system, and redo all the calculation by hands ourselves with the closed page of the book. There is no other way. It is necessary that you are aware and you are able to write those equations, those quantities, because you know, not because you have to derive from every time from scratch. All right? It is necessary that we are becoming familiar with all of that. And then the oscillation will be a frequency that is not exactly omega 0,2, because it is a little bit different. It is different because it is weighted by 1 minus the square on the non-dimensional damping. We should be also very aware that this correction is small, which is the amount of this correction, in which percentage is changing the natural frequency of the system because there is the contribution of a damper. Of course, this is 1 minus epsilon square root equal all right. So the quantity, so we open with the Taylor this expression, and so with respect to unity, the correction we are giving is 1/2 epsilon. And epsilon is the power of 2 of the non-dimensional damping. Which is the non-dimensional damping of a system that is decaying in this way? Number. We must have the numbers. How many cycles it takes to make 1/2 amplitude? It takes 1, 2, almost 3. All right? Almost 3. So if it takes 1 cycle to make 1/2, the H, the non-dimensional damping, when in 1 cycle I make 1/2, is 10%. Why? Because we make the calculation. We make the calculations and we must know those kind of things. So we must know that in case it takes 1 cycle to make 1/2 the amplitude, is because the non-dimensional damping is 0.1, 10%. If it takes 10 cycles to make 1/2, is because the damping is about 1%. All right, this is 1%, and this is 10%. All right. So in this case, it takes 1, 2, 3 cycles to make 1/2 the amplitude. It's about 1/3, 1/3 of 0.1, and so it is about 3%. All right. More or less, this is about 0.03. H2 about 0.03. 3% means 0.03. The square of 0.03 is 3, 10 minus 4. All right? This is 3, 10 minus 2. The square is 3, no, it is 9, sorry, is 9, 10 minus 4. And so it is 9, 10 minus 3. So, and so it should be about 1%. Is it correct? Yes, the square, I make the square of 0.03, it is 3, it makes 9, but I have to multiply by 10 minus 4. 10 minus 4, and so it is about 1, 10 minus 3. And so is about 1 over 1,000. No, it is 1 over 1,000. All right? Is 1 over 1,000. Is about 1 over 1. So the square of that is about 1 over 1,000. And so the quantity, the correction of the frequency is about 1/2 of 1 over 1,000, if I did not make mistake. So we must be aware that it is true. The damped system has a frequency that is lower than the non-damped system. But the question is how much? It is necessary that we have a quantitative vision of those kind of things, making simple calculation like that. And so we must be aware that this object here has a non-dimensional damping about 3%. So we must have it. We cannot become engineer doing courses on dynamics without having this kind of feelings. Okay? It is necessary. We are asking questions like that. And then it is necessary that we know that, all right, the theory is saying that the frequency becomes lower. All right, perfect, but how much lower? Almost not measurable, okay? It becomes much lower in case that there is a lot of damping. But in case there is a lot of damping, it is not a vibrating system. It is your car. Your car has a lot of damping, a little bit less than 1, but it is not a vibrating system. It is made in purpose in order that it doesn't vibrate on the bumpers of the road, all right? Anyway, all of that in order to say that there is a variation of frequency, but in case the system are vibrating, is because the level of damping is low, okay? And so for this reason, because of the level of damping is low, I give you the pen. All right, otherwise you cannot write. All right, so we are speaking about damping. We are adding a damper here. And we pretend to say that the fact that we are looking at is something like that. Well, but so we are speaking about things that are quite small, otherwise the system are not vibrating. If I am positioning here a damper that is very, very strong, I am blocking the system here, and so the system is no more a vibrating system, it's something that has a lot of damping there, and it becomes a fixed point almost, all right? And so in case we are continuing, we are speaking about a vibrating system, is because the vibrating behavior is still evident, the level of damping, and then the name must be correct. The level of non-dimensional damping, because if we are speaking about the level of damping, we are speaking about this number here. It doesn't matter which is this number, because it depends on the comparison with this number. Is the comparison among this number and that number that makes the trend of the shape of the trend of damping, of the decaying system, all right? And so what is happening, the system that we are studying are systems that are vibrating, and the system in which the level of non-dimensional damping is maximum some percent, 10%. 10%, it means that in one cycle, it makes 1/2 of amplitude, all right? So if the non-dimensional damping is 0.1, the system goes here, and then it goes here in the second cycle, and then it goes here in the third cycle, and then it goes here. So if the damping is like that, and we say, all right, it is incredibly damped, all right, it means 0.1. This behavior is 0.1 non-dimensional damping, all right? 10%. Well, because of that, because we are addressing systems like that are vibrating, and so the level of damping we are speaking about generally is small, then it happens that it is recognizable that there is the damping when I am looking to the behavior of a mode that instead of being totally not damped, then it has some damping, all right? So what happens because of the other additional terms that are appearing here is that coming from the same genesis, they are of the same magnitude. And so they are there. There is some dirty because of the effect of those modes. There is some coupling, all right? And so what is the effect of this coupling? Is that looking at the behavior of mode 2, together with that, I have something else associated to higher frequencies. Because there are the coupling terms of higher frequencies, higher modes that are getting into here and having and giving reasons to the quantity Qi star to put energy into the ith mode, all right? But the numbers that are running here are small at the same way that are small here for the specific mode that is going to be damped. And so there is some noise associated to the higher modes. If I am looking to the spectrum of the signal that I am reading here, so if I put an accelerometer here and I am reading, I will look to the presence also of higher modes, although I am exciting the second. So I want to excite the second. I excite the second with the natural frequency of an exciter, with the frequency of an exciter that is increasing the amplitude of the second mode. Then I leave it to damp down in the way that is working, that we described here. I'm looking to the signal of the behavior of the system, and into the spectrum, I'm looking to the second mode, but then I am looking to some dirty also of the other modes. But it is small. It is small because we are speaking about small quantities, and so unless very special cases in which we are adding a lot of damping, it happens that it is meaningful to speak about the increasing in the non-dimensional damping of mode 2, of mode 3, of mode 4, as they were not coupled to the others, also making application like that. So I'm a bit contradicting with what during the last lesson. Into the last lesson, the focus was it is coupling the modes, all right, and we are able to write. Then, from a quantitative point of view, we could also say I am feeling a lot of a clear effect into the specific mode that I'm looking at, all right? But the other modes, so the equation 2 is sensing the effect of the non-dimensional damping, the increase in non-dimensional damping into the mode 2. There is some crosstalk of the modes, so there is some noise coming from the other modes, all right? But it depends on the numbers, and so could be that into the behavior of the second mode, I can look at the behavior like that is becoming noised by the other modes, but there is not a total disruptive effect that is totally changing. It becomes like that in case the level of damping that I want to add is very, very large. So if I am adding a lot of damping, putting the non-dimensional damping of mode 2, pretending that the non-dimensional damping of mode 2 is becoming 20% or something like that, then all the modes are mixing together and I don't recognize them, and I'm not recognizing anymore the separated modes, all right? So it depends a bit on the numbers. All right, then, so please provide in order to be able to write this kind of things. And into the notes, I also proposed the note of in which way we write the response to an harmonic excitation, so the transfer function of the single mode, the two different ways in which it can be written. I uploaded the new slides associated to those things that are out of the general slides with some notes about that. All right, well, so the next point is that we spoke about the representation of the damping in terms of combination. So we go back to the n degree of freedom system. So we mentioned that, all right, there are concentrated dampers, but there are distributed dampers. So the system have an intrinsic damping because there are a distributed damping that is associated to the mass distribution and to the stiffness distribution. And we already learned into the n degree of freedom system that in order to give a practical representation of the effect of a distributed damping, we can address the problem pretending to represent the damping matrix associated to an n by an n degree of freedom system as a linear combination of the mass matrix and the stiffness matrix. So we learned this sentence. So we are proposing a damping matrix that is given like that. All of that could appear something that is a bit rude. So we have two real numbers that are taking care of the distribution of damping. So it will be a representation that is a bit far away from all the possibilities that can happen in a real system. All right, but the point is that we are speaking about the distributed damping, the mass, something that is associated to actually not to some concentrated elements, but to a general distribution of damping into the system. Typically, this hypothesis is very interesting, but it's very interesting because it is catching the point that where you have a lot of mass, you have a lot of damping. So if the damping is associated to something that is distributed into the system, is unavoidable that if you have more material, if you have more stiffness in those locations, you have more damping. But then the real point of this representation is that if we are moving into the principal coordinate, and making the transformation of coordinate, the transformation of coordinate is made by multiplying the mass matrix times the phi transpose matrix and the phi matrix that are the maximum of the eigenvector, and so plus beta, and here we repeat phi transposed stiffness matrix phi. All right, and this is alpha, and so this becomes R star. So the representation, the possible, if we are translating everything into principal coordinate, it happens that this matrix, so the matrix R star equal phi transposed phi transposed R becomes diagonal, is diagonal, all right? So if we are building this matrix that is full of numbers in this way, then it has a property that if I pre and post multiply this quantity by the transformation matrix, the matrix of the eigenvector, so the matrix made with the eigenvector positioned in this way and positioned in this way, it happens that all of that makes a diagonal matrix. And so it happens that in this hypothesis is an hypothesis that is associated to the idea. There is a strong association of this hypothesis of modeling of the non-dimension of the distributed damping that is connected to the idea that the distributed damping is not coupling the modes. So there is this, it is something that is coexistent. So maybe that is not the only way to make not coupling modes with distributed damping, but for sure it happens that if the distributed damping is following this modeling, then the modes are kept uncoupled, all right? And so what happens is that we are using exactly this hypothesis for the continuum, and in case we have a continuum, and in this continuum we have a modal mass m star, and we have a modal stiffness k star, we are saying that the Taylor hypothesis is saying that we can add a diagonal damping matrix made as alpha m star plus beta k star. It means that I calculated for the specific problem of our continuum the modal masses, the stiffness, the modal masses, the stiffness, the modal masses 1, 2, 3, 4 for the different modes, the modal stiffness 1, 2, 3, 4. So I have those numbers. So I have the numbers that are coming from the analysis of the problem from the elastic solution of the problem. With those numbers, I am building other numbers that pretend to be representative of the non-dimensional, of the dimensional damping of the associated to the different modes and associated to the distributed damping into the material. All right. For which reason, in which reason we can make an utility from an hypothesis like that? Because the point is, but who is giving us those numbers? From where those numbers can come? And which is the connection of those numbers with the real behavior of the system? There is a very quick connection that can be shown, and that it can be represented in this way. So we have to deal with what is intrinsically the meaningful for the damping, not the dimensional damping, but the non-dimensional damping. And so we must write things in terms of non-dimensional damping associated to the mode I, given the hypothesis that we made. And so we have to divide by the critical damping. And which is the critical damping? Critical damping associated to the mode I is 2 times m star of the mode 2 multiplied omega 0, 2. All right? Always. The critical damping is twice the mass of this 1 degree of freedom system multiplied by the natural frequency. And so it makes alpha. So I wrote 2 because I was working with this exercise, but we are speaking about the ith element, all right? The ith element. All right, so hi star will be equal to 1/2 So this hypothesis is associated to a distribution of non-dimensional damping that goes hyperbolic with alpha, that is the contribution of the mass. So we say we have damping because there is a mass distribution. Because of the mass, the effect is hyperbolic. So the non-dimensional damping goes like that, in case we are speaking about the contribution of damping associated to the distribution of mass. Please note that we are not speaking about the modeling, the physical modeling. The physical modeling is too difficult. There are someone who are addressing all of that. We are not addressing. We are making a modeling that is a higher level. So the Taylor modeling that is meaningful because the structures are following this kind of behavior. And so this quantity is alpha. And this is the term that is associated to beta. Associated to the stiffness. And so the expected behavior is something that is the addition of a behavior like that plus a behavior like that. Well, of course, if we could be that this number is 0, or is a big number, or it could be that this number maybe is much larger than that. And so the prevailing behavior could be associated to the linear trend increasing or to the hyperbolic trend. For sure, we read that this is going to be 0, finally, and this is growing. And so we are, for sure, so a modeling like that, for sure, is saying that the higher modes somehow have more damping than the lower modes. But at the same time, is saying that is not mandatory that the lowest modes have the lowest damping. And so if we have a structure and we have access to the structure and the structures are monitored, and so we can learn from the real world in which way the structures are behaving, and those modeling are coming from the monitoring of the real structure. Could be that we are measuring the non-dimensional damping of the first mode. Then we are measuring the non-dimensional damping of the second mode. We are measuring the non-dimensional damping of the third mode. We are measuring the non-dimensional damping of the fourth mode and fifth mode, and so on. And we could have done all of that without making the modeling, but just putting the note of what we did, what we measured into the experiments on the structure, and then we make a regression, and this regression has a behavior that generally goes like that, and generally the minimum is not at the first mode. And so that the way in which the numbers can be modeled, alpha and beta, typically follows the reality of the typology of structure. And so the most that you could find into the scientific and technical literature is maybe some studies that are pretending to propose a possible modeling alpha m plus beta k for some typology of structures, but actually there is not much around. So there is something around. But the Eurocode is saying for well-built steel structures welded, the non-dimensional damping that should be accounted for is 3 over 1,000. 3, so 0.3%. And it is saying just that. Then it is giving some other numbers. But a modeling like that is, for the technical application, is something that is quite valuable. So if you are looking to the literature, scientific and technical literature, in order to find results and in order to feed a very simple model like that with numbers, you are with a great surprise, you don't find much. Because it's difficult. It's difficult anyway, or because just because whenever someone is getting his number, he's keeping. All right. An example. When the Stolbel Bridge was inaugurated, 1998, something like that. The Stolbel Bridge is the longest bridge in Europe, if we are forgetting the Çanakkale Bridge that is connecting over the Dardanelles Straits, Europe with Asia in Turkey. Okay, so in Europe, in Denmark, there is a bridge that is the longest in this moment, 1,600 meters. So before, at the same time that it was built, it started moving because of the vortex-induced vibration. And then it was fixed. So it was fixed by guide vanes positioned here and there. It was a little bit expected, but anyway. So it started vibrating in the meanwhile, soon as it was built. And then with the guide vanes was fixed the problem. And which frequency was running? The fifth mode, the third mode, third, fourth mode. Then recently, when the Çanakkale Bridge was built during the construction, also there some VIV behavior happened, but before finishing to build it, and again it was at higher frequency. And so in all the time that you are looking at some malfunctioning of big structures due to typically to excitation to vortex shedding, not buildings, big structures with higher modes that are working in the same way as the other modes. typically the VIV of very long span bridges is happening not at the first modes, it's happening at the higher modes, not the 10th mode, the 3rd, the 4th, and all of that sounds in agreement with the Mr. Taylor is happy because of that, all right? Very well, so those were comments. I took some notes. There are some notes, and I try to spend really short time. So the expected non-dimensional damping of the Messina Strait Bridge is less than 0.3%. So in the calculation we must assume 3/1000 by the Eurocode, but the expected could be less. All right, we started discussing those things, speaking about the big building, the tall building, and actually the idea was to pay attention to something that is here in Milano, that is the Isozaki building. Sorry. All right, well, and so there are the legs, but the legs are very interesting because we can speak about the kinematics, and so the kinematics is interesting in order to speak about the links and the way in which we are calculating the possible numbers. But then, at first, so most of the very tall buildings are working in a totally different way. So there are a tuned mass damper on top of the building. So there is an oscillating mass positioned on top. And tuned means that it's tuned. What does it mean, tuned? It means that it is oscillating intrinsically at the same frequency of the building, making so that when the building is moving at that frequency, that is at the frequency that we want to protect, so when the building is moving at the frequency that we want to protect, this motion that is given to the constraint of the mass is exciting the resonance of the mass. So the mass is vibrating a lot. So the amplitude of mass with respect to the building becomes large. So the damper that is positioned into here is dissipating the energy, and so it is increasing the non-dimensional damping of the mode that has been excited. All right, is it clear? So the tuned mass damper works in this way. It is plenty of examples. You can find out all the examples of tuned mass damper around the world in the very tall buildings. Very interesting. All right, but there is, I would like that someone is telling me, but what happens when I'm positioning a mass like that on top, tuned more or less at the same frequency of the mode 1 that I want to protect? From the analytical behavior of our studies, what happens? It happens that the mode 1 we are speaking about is disappearing. It's no more there. It's disappearing because it is here. It is a really, let's say, coupled to the mode of the oscillating mass. In purpose, we are tuning the frequency of this mass. So in purpose we make so that the natural frequency of the mass. With respect of ground, so we make so that Kd, so this is Md bad drawing. So in purpose, we make so that the intrinsic natural frequency of the mass of the damper with respect to ground, so it makes the hypothesis that we are fixing this object to the ground and we are learning how it works. So we are designing, we are preparing this object to be positioned on top of here, all right? We make so that the omega so we are dimensioning this object so that the intrinsic natural frequency K damper divided mass damper is equal to omega 0 damper square with omega 0 damper almost similar to omega 01, to where omega 01 is the natural frequency of the first mode of the structure that you want to protect, all right? Then we are not going more in deep about that. In which, about plus minus 5%. So we make not exactly equal in a little bit less or a little bit higher than the one of the object that we want to protect, all right? But it is tuned, okay? So we tuned in order that it has a frequency like that, not far from the one of the object that we want to protect. At this point, if we want to make the modeling of the system, the modeling of the system will be, and now I make a drawing, and then I will have to justify this drawing. All right, this is the drawing. The drawing is, we are modeling the object with the model representation of the first mode of the structure. And so we are considering the equation where we have the mode 1 that is running, but we are coupling this mode 1. This mode 1 here is represented by the modal mass of mode 1 that is connected to ground through the stiffness, that is the modal stiffness of mode 1, is connected to ground with the damper, that is the modal dampy of mode 1. And the point is that this object is not enough. So the modal dampy of mode 1 is not enough. We want to increase it, okay? We want to increase. In order to increase, we are connecting to the system, to mode 1, but we actually we are connected to the structure. We are connected to a structure, a physical object that is this damper. This damper, if it was connected to ground, it has a frequency that is very, very similar to the natural frequency that we want to protect, plus minus 5%, very, very close, incredibly close, very close. So that when the first mode of the structure is vibrating, it makes resonant the tune mass damper. And so the tune mass damper will move a lot when the system is moving along the first natural frequency, all right? And it will dissipate. So this is the way in which the system is working. All right, very first I would like that you are confident with the model representation like that of the problem, and confident with the number that we have to give to this model mass here, in order that this number that we are giving here is consistent with the drawing where the movement that is filling the damper is the movement of a location here, that is the location there of the structure. So we want that here into this very simple modeling, the movement of the mass m star 1 is the movement of the top of the building, all right? And so the point is that we have to refer to the first mode of the structure. Now, referring to the first mode of the structure, in order to simplify the discussion, we make reference to a share-like deformed share-like first mode, so something like that. So as the deformation was just a shear deformation, we want to make it the most simple as possible. It is wrong. Yes, it is a bit wrong because instead the structure has a behavior that here is like that, but let's forget, it doesn't change much, all right? So let's make reference to a mode like that. And making reference to a mode like that, let's say we are making reference to a representation where this is x, this is y, and we are representing the mode with phi 1x almost x divided by L. With this choice, we are saying that at the location L, the movement, at the location L, the deformed shape is normalized to 1, all right? So we are saying phi 1x equal L equal 1. So here we are working with the numbers. We are giving a normalization to the mode. We are normalizing the mode so that it is equal to 1 when we are looking at the maximum, the point of the maximum deflection, all right? But which is the connection of this normalization to 1 with this modeling here that we are speaking here about? Why the two things are connected? But because when we are saying that the mode is working, we write the equation of the mode M1 star Q1 two dots plus R1 star Q1 dot plus K1 star Q1 equal 0, and this is the free motion, all right? Well, which is the meaning of the principal coordinate Q1? So we write y x t equal phi 1 x q1 times q phi 2 function of x multiplying q2 times q plus and whatever. But we are focused here. Who is q1? When we are normalizing to 1 the model shape here. If I am representing a diagram function of time Q1 function of time. I make a simulation, and in this simulation, this is the function Q1 function of time. About who am I speaking when I say Q1? Who is moving with the Q? Who is moving exactly with the amplitude Q1? The spot of the structure that has 1 for the model shape. If I have a location in the model shape that has phi x equal 1, this spot here is moving exactly like the principal coordinate. So here we are touching with our hands that the normalization of the model shape is extremely relevant, because if I am normalizing the model shape in this way, so that when I am at the top of the building with x equal to L, the model shape is equal to 1, under this hypothesis, and I make all my calculation with this hypothesis, as a consequence of that, the function Q1, function of time, is not something that is far away just in the world of the ideas. It's something very practical. Is the magnitude of the motion of the top of the building. So the normalization of the model shapes is extremely relevant in the real world, in the practical world, because we are deciding with the normalization we are deciding in which way we are speaking about the structure, and who is, and about what is representative, the motion that is let's say, described by the principal coordinate. The principal coordinate Q1 now, with this normalization, has a very physical, practical, evident meaning. Is the movement of the top of the building. That's it, it's finished. And it is, so making a normalization different than that is possible, but it is, I would say, stupid, not useful. Let's say it is making us in troubles instead of making us in a simple way of thinking, all right? If I do a normalization like that, it's clear. Who is Q1? The movement of the top of the building, finished. And in the normalization that I have to do, making the mass oscillate with respect of the model behavior of the building, and trying to mount the modeling of this object, inclusive of the tune mass damper, in which way I can work. But simply saying that I have a mass, that is the model mass of the structure, calculated under this hypothesis, of course. And the model mass, we have to remember that m star 1 is integral 0L mass function of x phi 1 square x dx. So I am calculating a number here, but I have numbers into here. And the number that I am calculating here is consequent to this choice. And so the number that I have to give to this modeling here is consequent to the selection of having model with the hypothesis that the movement is equal to 1, the shape is equal to 1 on top, because it is useful. It is not, we are not obliged to do it, but it is useful, and so we do it. And it gives a physical meaning to what we do. So we do that, and so it is meaningful to have to give a modeling like that, to say that I have one mass M1 star, and another mass like that connected by exactly by those stiffnesses and damping that I have here. All right? And so this is a very simple model of this object, taking advantage of the model representation of the building, using just one mode, that is enough, because we want to protect that, and adding the TMD. All right, numbers. Let's calculate the model mass 1. let's use m as the mass per unit length. So we make the hypothesis that the mass per unit length is constant, all right? Try to follow me. Mass per unit length, modal shape, x divided by L, square, integrated over dx, 0L. All right. M star 1 equal m L square 1/2. All right? No. So the integral of x square is 1/3 x power of 3, all right? 1/3 x power of 3, calculated from 0 and L makes L3, L power of 3. Is it clear? Not too difficult? No. Well, equal 1/3 So the hypothesis of the share-like deformed shape mod 1 is useful in order to make this integral easy, but meaningful. Is meaningful, all right? So the modal mass associated to mod 1 is not the total mass, because the system is not moving here, and it is moving 1 over here. So the contribution of the distributed mass is 1 here, but then it can lower, and it is 0 here. And so the reason for making meaningful normalization of the modes is at the purpose of making meaningful representation of the numbers, for example, of the modal mass. So it is very meaningful to say that the participating mass in this mode, it is not 1, is 1/3. 1/3 of what? Of the total under the hypothesis of uniform distributed mass. Very well. The Isozaki building, the total weight of the Isozaki building is about is about 100,000 tons, all right? It's about 100,000 tons, more or less. So maybe the numbers, no, this is the number that I have in mind that is a meaningful number for an object like that. And so it makes that M1 star is about 30,000 tons. So this object is 30,000. I write tons because otherwise it's a too big number in order to have a physical meaning of what it's about. All right, now we are so into the notes. There are I wrote also the equations. So there is the equation of this 2 degree of freedom system. All right. If you want to write the equation of this 2 degree of freedom system, in which way you do it? Apply Lagrange equation? Yes. All right. But I suggest you to check the equation that are written here. Apply a mechanical approach. The very mechanical approach is to say there is this system that is moving with a certain acceleration. So I give a general displacement to the system. So I give a displacement in terms of a variation of the position, a variation of the velocity, a variation of the acceleration. I apply the numbers. And so because of a variation of acceleration, I have an inertia here associated to the coordinate acceleration of this mass. and inertia here associated to the acceleration of that mass, all right? The acceleration of that mass is the addition of this, of Q1 two dots plus X D two dots. So this is Q1 and this is XD. In my opinion, into the drawings here, I wrote this Q1 as X1. So Q1 is the principal coordinate here, but then I write here Q1 is equivalent, is totally equal to Q, and the equation are written as X1 and X damping. So, all right. So in the equation, I just would like to say that you have the total inertial forces that are counteracted by the stiffness here and the damping here. This gives an internal force to the system. So if my system is mass 1 plus mass damper, I have the total inertia and just those two forces. And then I write the equation of just the damper, and in the equation of just the damper, I have that the acceleration of the system is the relative coordinate acceleration plus this the acceleration of x1, and then the stiffness and damping forces are just those. So if you read the equations, so I would like that you read in the equation. The first equation is the equilibrium of the full system, and where there are the acceleration of the two and just the forces coming from here. The second equation is just the equilibrium of this mass with the acceleration, that is the total acceleration given the relative motion plus the motion of the M1 and just the forces that are coming here. Without writing the, if you write the Lagrange equation, it comes exactly the same result. All right, this equation shows that the system is a 2-degree of freedom system where there is a coordinate that is x1, that is the motion of the top of the building, and that is q1, and a coordinate that is x damper, that is the relative motion of the damper with respect to the building. I write two equations, and so it is a 2-degree of freedom system, and so the behavior of this object will be a behavior like that, where I recognize two peaks, where there is a peak I have two natural frequencies, all right? I have two natural frequencies because it is a 2-degree of freedom system. If I select, then the tuning of the system is to select the natural frequency of the damper and the natural frequency of the system that are very close each other in order to make those two peaks that are a bit merging together, so that the overall behavior of this 2-degree of freedom system is looked at by the structure as an increase of the modal damping of the mode 1 of the structure. So we are adding another mode, and the two modes are mixed together, but let's say that here we have two eigenvectors, two eigenfunctions, two eigenfrequencies, and two non-dimensional damping, all right? So then the point of estimating from this 2-degree of freedom system the effect in terms of non-dimensional damping of this mode that is increased by this damper is a bit tricky. We are not discussing, all right, but it's possible to discuss. So the discussion of the TMD, it goes into the discussion of this 2-degree of freedom system that is mixing the modal damping of the mode 1 plus the mode of the TMD with respect of mode 1 that are mixing together, and then finally the modal behavior of mode 1 of the structure shows an increase of its non-dimensional damp. The rule of the thumb for this behavior is that the maximum increase delta H1 max percent is about twice the increase of mass associated to the damper. Let's speak exactly what do we mean. This quantity is mass of the damper divided m star 1. So we say that if I have a modal mass of this object of 30,000 tons, of course, normalized here. So now we are speaking about those numbers, and the number is 30,000 tons m star 1, all right? M star 1 with the symbology that we give. So we say, I have a modal mass of mod 1 that is 30,000 tons. All right, but this number is meaningful because we spoke about a normalization mod equal to 1 here, modal shape, estimate of the modal mass, calculating the model, using the representation of the modal mass through the modal shape. So all of that is connected. So because of those reasons, I can speak about a number here. And so I have the 30,000 tons here. And I say how much I put here in terms of damper. 500 tons. So 500 is an added mass of 1.6%. You divide 5 by 3, so you have to say 5 divided by 300, all right? And so it is 5 divided by 3, that makes 1.6, and then divided by 100. So it is 1.6%. So we are adding a mass that is, let's say, if it was 2%, if we are adding a mass that is 2% of the modal mass, the maximum increase in non-dimensional damping is twice this percentage. It will be 4%. All right? So the rule of thumb of the tune mass damper is that when it is best tuned, and then there is another point that we didn't discuss yet. The value of the damping with which it is connected to the building, all right? So under the hypothesis that it is, there is an optimum tuning, and the order, so the natural frequency of the tune mass damping with respect of ground is in the order of some percent different from the frequency of the model that we have to tune. Then, second hypothesis, H star H of non-dimensional damping of the damper is about 10%. So the best tuning, so it is 0.1, non-dimensional damping equal to 0.1, that is 10%, all right? H damper 0.1, that is 10%. Under the hypothesis, so the top that we can get is the best tuning in this range, some percent out of the frequency of that we want to protect. Intrinsic damping of the damper, 10%. With this object, we can obtain an increase of the non-dimensional damping of the protected structure that is twice the increase of mass that we are giving to the object. So the delta mass is the 500 tons of steel of the mass of the damper divided 30,000. And so for the design of this the Isozaki, one of the possibility was to make a TMD of 500 tons that with respect of the 30,000 tons makes 1.6%. The intrinsic damping of the building is intrinsically about 1.5% plus 2 times 1.6 makes 1.6 twice is 3.2. 3.2 plus 1.5 means 4 by 7. About 4 by 7%. And so the point, the idea was using an object with a mass that is in the order of, we said, 1.6% of the model mass, be careful. 1.6%, not of the total of the 100,000 tons of the model mass, of course, okay? 1%, 1.6%, so this percentage is over the model, all right? So this is the rule of thumb of dimensioning of the tube mass damper, and so the idea, if you are looking at the buildings, if you ask ChatGPT, which are the dimensioning of the tube mass dampers of the building around the world, it will tell you numbers like that, some 100 tons, typically. It is, and the reason is that the more or less the total mass of the building, but we speak about buildings in the height of 200 meters. So if we speak about buildings of 400 meters, it's different, all right? But this is the way in which we are, so the way in which we are using the model approach is this one. So, you know, we are using the model approach in order to make very simple the calculation, to make very meaningful. So there is a lot of theory behind, yes, all right, but in order to have the feeling of what you're doing, and the feeling of what you're doing is done making the calculation by hands, using the numbers, having the idea of the number that we are using, that we are working with, all right? And so I suggest that you try to become confident with those numbers. Into the slides, those things are written. And this, in my opinion, it is an interesting example. So it is an object that is here. And you have the idea, the feeling that the total mass of this object, of the building, is so the numbers are very easy also. 100,000 tons is easy number. And the TMD, 500 tons, that is an easy number. Which is the volume of 500 tons? Still, ask ChatGPT. It gives you the answer in 3 seconds. Or do it the calculation by. So it is 4 tons. It is 1 cubic meter is 7 point something tons. And so the 500. So which is the size of of a cubic or a parallelepiped object having 500 tons? It's not very much large. It's not very big. Anyway, the real point for those things is that they are using the volume in the location that is worth something like more than 20,000 euros square meter. Selling the apartment, of course, we are speaking about that. And so it is competing with the need to sell the ground. Right, so the real cost of the TMD is not the technical cost of the TMD. It's the lost space to be sold for the apartment. All right. The new trend, but still not very, with not much of application, not many application, is to use not more passive tube mass damper, but active dampers. All right, so the idea the idea is to, but this is what is what your colleague mechatronics are doing. So to work with mechatronics and to position here a mass that is driven by an actuator, and to make this actuator working in feedback with respect of the movement. And so using an active mass damper that is moved by an actuator, you can do exactly the same thing. So you can make an inertial force that is giving a force that is in 90 degrees of phase with respect of the movement that is emulating a damping. And so you can make an artificial and active object that is doing the same job. And this is the step that is running now. If you look at in the web, to the name is Torre Piloti Genova. Torre Piloti Genova. It is a very, very light structure that is the new Torre Piloti in the harbor of Genova. That is like a, it is extremely light, and it is very sensitive to the wind effect in both in torsional motion as well as in the bending motion. So it is like the mast. So it is an object. The best is that you are looking at the Torre Piloti Genova into the web. It is very light, and it is very sensitive to the wind effects. The way in which it is made safe with respect of the excitation of the wind, vortex-induced vibration, as well as possible other behaviors, is through 4 active mass dampers that are that are protecting both torsional as well as lateral bending modes of the structure. It is an interesting example, and it was the first realization of a system like that. So in Italy there are not many structures like that, and this object, so the system was done by young people like you, who made a new company. They did the PhD with our group, and then they founded a company working in active mass dampers. They worked a lot on the seismic application of the active mass dampers, and then they moved into the possible application into the wind effect, and we are collaborating with them. And this is a very interesting story. So the name is ISAAC, ISAAC. This is a new company that is coming from Politecnico. It is 10 years ago they were students like you, and so they are responsible of the damping of the structure. That is quite interesting because it was a critical structure. All right. We have a little bit of time to speak about, to go back to the theory, what we are missing. We are missing the orthogonality. All right, this is the object. We speak about a beam. The partial differential equation that is driving the behavior is this one. the free motion of the structure is given by and be careful, here we are not making the model approach. Here we are writing the free motion. And those are actually the harmonic functions that are representative of the free motion. And so they are harmonic functions that are oscillating at the natural frequencies of the modes, all right? And in particular, gi two dots divided gi is equal minus omega 0 I squared. So we have the material. We have the movement into the vertical plane. We write the equilibrium of the infinitesimal element. And we write, because of that, the equilibrium of the infinitesimal element with respect of the inertial forces and the differential of the shear. And we write the partial differential equation. Then we say, I have constraints. We have some constraints, not necessarily those constraints. It can be the very general typology of constraints. And into the demonstration, we are using the very general typology of constraints. But we are adding the constraints. Having added the constraints, the model shapes are born and the natural frequencies are born. And it happens that we can write all of that in this way. So up to here, we are just saying, we are speaking about mode I. We are speaking about mode I. So we are speaking about the generic ith mode, but the behavior is done making the superposition of all the modes, all right? So here we are. For the ith mode, we can write that the solution phi, together with the function of time gi, are satisfying this equation. Second means derivative of the second order. Second makes derivative of second order with respect of space. You take out this because it is a constant with respect of the derivative with respect of space, all right? Derivative with respect of space, here function of time, it gets out, it's like a constant. I put this down here, gi, I cancel here. This makes minus omega 0 squared, all right? And so we can write this as, here becomes minus omega 0 squared, but I put it in the other side of the equation, and so I write equal, the minus becomes plus, because it is in the other side. I cancel this, and I write omega 0 I squared, all right? So all of that is already totally done because we did it. But we are repeating, we are writing back again the same things. Now we cancel this. Second. All right. This is the starting point. So we say, we can write this equation for the mode I, but we can write also for another mode, for mode J. And be careful, here I have omega 0I, here I have omega 0j. The only difference is that this is function phi j, and this is function phi j, and that's it, is equal. This is equal to that. Now, what we do? We multiply the first equation by phi j x. So we multiply left and right by phi j. And so we write that this is times phi j equal phi j. But be careful, it was omega 0I squared here, all right? Because we were starting with I. Here we do exactly the same, and here we multiply phi I function of x equal and so they are very equal unless here is I and here is j, here is j, here is I, j, I, j, I, j, j, I, omega 0I, omega 0j. All right? What we did, we wrote that they are that those functions are satisfying the PDA, are satisfying the boundary condition, and actually there is omega 0I here. And then I am multiplying. For which reason we are multiplying like that? But because if now I write here integral 0L over dx, what is that? The model mass ij. This object here, I recognize that this object here is m star ij. All right? I do the same here. And of course, I have to say that I do the same here. And here there is not much space, but all right. So here I recognize m star ij. This is m star ji, and this is not. This is sounds like the modal stiffness, but is actually is not exactly the modal stiffness. Well, now we have to remind that if we have integral let's do like that. You remember this, the integration by parts, it was learned like that by you. You have a function that is the derivative of something. So if you recognize that you have the product of two functions, and this is the derivative of another function, you can write that this is equal to, all right? Is it clear what I did? The integration by part is you have a function. You recognize that this is the derivative of something. And so you can write this like that. All of that comes from f, g, first. So it comes from here. And you make the integral of this equal the integral of that equal the integral of that. This is fg 0L equal integral f first g dx plus integral f g first dx 0L. Okay, this is the demonstration. So the demonstration of this is that. So you have the product of something, the derivative integral, it makes the part that is getting out. So it is the integral by parts. It comes from the derivative of a product that is the derivative of the first times the second, the first not the derivative multiplied the derivative of the second, integral of the two parts, it makes exactly what we wrote. Exactly. Integration by part. The integration by part recognize that here you have a second order derivative. In order to go ahead with this object, you write that, let's say that this object is written as E, J, Z, function of x, phi second, I, function of x, first, phi jx, so let's recognize what we did. This second becomes first, it goes back of one order of derivation. It is like that, like there. So here you have f first. F first, it goes out, it goes back one order of derivation, and so you are calculating outside this, that is the back one order of derivation, this multiplied by g to the extremities. Integral of, we are transferring the order of derivation to the other function. So you write f and g first. You are switching. So you are going back in the order of derivation with f, and you are going ahead with the order of derivation with the g. All right? This is the principle of the derivation by part. And so this is the step. This is the step that you do. Then you do a second step. Then you work exactly in the same way, going ahead with this step. Let's recognize, and then we stop here and we go ahead the next time, but let's recognize that if I have whatever is the boundary condition, so whatever is the boundary condition, let's consider one extremity of a beam. If the beam is free, what happens? This is the shear. The shear is null, and so this quantity goes there. If the constraint is a constraint like that, again, the shear is null. This is null. If the constraint is a hinge, the moment is null. No, the displacement is null, and so this goes to 0. If the constraint is a totally fixed, the shear is not null, the displacement is null. And so what is out of the integral calculated at the boundaries follows the boundary condition. So the functions that we are speaking about are coming, are satisfying the boundary condition. And so we are asked them to satisfy the boundary condition so that what is getting out from the integral during the integral by parts is null. The next step that you do here is again the same. Having done the second step, what you get here, what you get as a result, having done the second step, is, and then we finish here, is E, J, Z, function of x, phi I second x, phi J second x, dx, integrated 0L. So what I said is we go back of 1 and we get not derived, this quantity. And we go ahead with the 1 here and we have a second order. And what is that? This integral is k star I, j. All right? And so finally, we making the integration by part, we are working out and finishing this procedure, saying that the k star ij is, on the left side, is equal to integral 0L m function of x phi I x phi j x dx omega 0 I squared. All right, so we are finishing what is going out of the integral with the boundary condition goes to 0, and we are finishing like that. In the second equation, it is exactly the same. Switching here, it is exactly the same, but instead of having omega 0 I square, we have omega 0 j square. This is a contradiction. That is asked that in case I and j are not equal, the values is equal to 0. Because what we do, we are subtracting this equation from the second equation, and so we are saying that what we do the next time. But the core of the problem is to start with the partial differential equation, to substitute and to write the functions that are satisfying the boundary condition, and so apply that those functions are satisfying the boundary condition, but we make the trick of multiplying the first equation times the second modal shape, the second equation times the first modal shapes, in order to build in purpose, we are building the model mass. And here, into here, working with the derivation by parts, we are getting out some elements and finishing with the model stiffness. And so we write model stiffness equal to model mass multiply omega 0I. And then we write the same model stiffness equal to the same model mass multiply omega j. The only possibility that all of that is working is that it is the model mass or model stiffness that in the mixed term is null. So it is making all of that under the hypothesis that omega 0I and omega 0j are different. Anyway, this is, so we didn't have the time, but today we just put the first steps. Then I hope that you have some ideas. You read the demonstration. It is easy. It is extremely easy. The only mathematical trick is the derivation by part, but the integral by part. But the integral by part is the rule of the derivative. Is that this? And so there is not a strong mathematics. It's more interesting to follow than the intuitive vision. Then we repeat. We spend the next time half an hour on that, and but please try to read it. All right, we stop here. Sorry for having taken a little bit of time.